number 11. So
Okay.
we are very happy because very good response from the all faculties. There are about 200 participants is there for the particular that session.
Okay.
Okay, so I just give introductory speech and let we start.
Okay. Okay.
So, Rajendra Pawar, Faculty of Civil Engineering Department, DSUA Karad. It's my honor to introduce today's our distinguished resource person, Professor Abhijeet Bhondave sir. Professor Bhondave is currently serving as Assistant Professor in Department of Civil Engineering at Government College of Engineering, Karad, Maharashtra. A position he has been holding since December 2015. He brings with him a strong academic background and rich research experience that bridges geology with modern civil engineering application. He completed his MSc in Applied Geology in 2012 and has demonstrated academic excellence by qualifying prestigious national examinations such as CSIR with an All India rank 27 and GATE in Geology and Geophysics. Before joining Government College of Engineering, Karad, he served as assistant professor at RTM Nagpur University and also worked as a project assistant at CSIR National Geophysical Research Institute NGRI Hyderabad, contributing a nationally and internationally funded research project. His research interests includes engineering geology, remote sensing and GIS, and igneous geochemistry. Currently, he is involved in advanced research at IIT Varanasi, focusing on petrogenesis and tectonic setting of ultramafic and mafic rock of southwestern Maharashtra. He has also worked on World Bank funded project related to aquifer characterization using advanced geophysical techniques. Professor Bhondave has several research publications to his credit, including journal articles and conference paper. He actively participates in academic development activity such as workshop, STTP, FDP. He is a life member of Indian Society of Remote Sensing and the Gondwana Geological Society, reflecting his active engagement with scientific communities. With his strong academic foundation, interdisciplinary expertise, and commitment to teaching and research, we are truly fortunate to have him with us today. Let us warmly welcome Professor Abhijeet Bhondave sir and look forward to an insightful and enriching session. Now I request sir to take charge. Please sir.
Okay. Okay. Thank you so much for this introduction.
Yes
Kindly
sir.
let me know if my content is
Sir, yeah,
visible.
I think your camera is on, but you're not sharing still. Yes, your
Uh,
PPT now visible, and your sound
okay.
also strongly audible.
Okay.
So you can start, sir,
Okay.
please.
Okay. So I think now it's quite clearly seen in the landscape mode. Okay. So good afternoon to one and all. It's pleasure to be back to the Maharashtra because I was here in IIT BHU, Varanasi for last 2.5 years, and now I'm grateful to the developer of Higher College of Engineering for giving me this opportunity to present a topic and have a discussion probably with the entire fraternity of the faculties across Maharashtra as well as in India. So this is the topic that I will today discuss with a little bit because since the our FDP is on industry academia synergy with the disaster management on the focus, so I'll try to get this continental drift plate tectonics, which is a typically a geological topic, to match with the engineering terms. So let's begin. So these are my contents. Basically, I'll be discussing the internal structure of the Earth. Probably this would have been discussed by Professor P.K. Deshpande sir probably a day before yesterday. And a short, that's why I will take a review. Then how the Earth is a dynamic planet, because that's what we are as an engineer interested in, because our entire infrastructure, the dams, bridges, all are resting on the Earth, and the stability as well as the strength of all the structure depends on the Earth's stability. And we have also seen, because this concept probably has discussed the earthquakes and landslides and all those things. So that means Earth is not the rigid the way we think. So it's a dynamic planet. So how it is, that I'll discuss in the second part, followed by the topic of the presentation, that is continental drift theory. Then its evolved version with the enhanced evidences as theory of plate tectonics. Then certain what are the output of these continental drift and plate tectonics? What are the events that are typically caused by these two phenomena? I'll discuss that. And lastly, a couple of case studies which will bridge this gap of, say, geology and the engineering, how it is applied in the engineering terms. So first, to start with is the structure of the Earth. Probably all of you know in a broad idea that Earth, as the crust, is the topmost layer, which is a solid in state, followed by the mantle, and followed by the core. So these are the three main layers of the Earth. The crust is the rigid out layer, but it is thin. If we take an example of an apple, the skin of apple will probably reflect the crust. It's very, very thin, 35 to say, I mean, on the continental crust, it is thinner, it is rather thicker. It is 35 kilometers to 50 kilometers. Say in the Himalayan region, there is another theory called AICTE. I will not go in detail of that, but on the Himalayan region or the mountainous region, the thickness of the crust is roughly around 50 to 70 kilometers. And for the normal land masses, the continental thickness is roughly around 35 kilometers, meaning that Moho is the discontinuity is being said to have. And the thickness of the crust on the ocean floor is 8 to 10 kilometers. So, the radius of the Earth is 6,400 kilometers. Now, 6,400 kilometers at one side, and the thickness of the crust is somewhere between 35 to 50 kilometers, which indicates how thin the solid part is there on the Earth. Now, beneath that, from say 50 kilometers, or 35 actually, but say in safer side, 50 kilometers, 2,900 kilometers is the vast plastic molten material, not exactly liquid, but molten, more of a plastic nature, and that is called as mantle. Okay, now this mantle is very, very crucial when we are discussing this continental drift and the plate tectonics, because all these phenomena, the movement of the continent, is being governed by this mantle phase. Okay, so this is plastic thing on which the continent and ocean floats, if I can say in a layman terms. Beneath that, after the 2,900 kilometers to 6,400 is core, very hot, high density. Yes, one more thing. Crust is having the least density. And then as you go inside, the more and more it gets denser. So the density of, say, crust is something 2.75 to 3. Then you go up to mantle, goes on increasing up to 6, 7. And then in the core, it can reach up to 11 to 12. Okay, so this is how the density varies. It goes on, density also increases towards the core, as well as the temperature also increases from the core to core. Okay, the crust is normal temperature. As you go inside, mantle is hot up to 400, 500, 600, and then you go inside deeper and deeper, it will go up to 1,000 and 1,200 degrees Celsius. And as you enter into the innermost core, it is very hot up to, say, 4,000, 5,000 degrees Celsius. It is just like as hot as the Earth, the sun's outer sphere. Okay, so this much is the hot inside the Earth. So now this core is of, say, the outer core is thought to be of liquid because the P wave and S wave cannot be propagated. So we will discuss this later. And the inner core is thought to be in the very solid state or a plasma state. There is a debate whether it is a plasma state or solid state, but for, in say, a simpler term, we can say it's a solid, acts as dynamo. The reason the core is very, very important because it is made up of nickel iron type of ferromagnetic material, which eventually make Earth a magnetic planet, and we have magnetic shield because of this core. Okay, so from our point of view, these are the three things. Out of that, as a civil engineer, what is for us very important is the crust, because our structures rely or rest on the Earth's crustal part. But this crust floats on the mantle. Henceforth, mantle and crust are the two things which are very, very important. Okay. Now, how come we know about all of this? Okay, how this? I mean, crust is fine. We clearly observe, but what is there inside mantle? It's in plastic state and it is hot. And how come we know all this? So there are two ways to know. There is direct evidence and indirect evidence. So direct evidence is that volcanoes are our laboratory where we can get to know about what is inside the earth. The lava comes out, it flows, it indicates that inside the earth, it is not entirely a in the solid state. There is some liquid or plastic material is there, which is very hot when it comes out. So therefore, these are the clear ideas. As a scientist, some of the geoscientists or this sample this lava and then they do different tests on those lava and we come to know about the all this property, density and all the chemical characterization also. So this is one way, but it has a very limitation because how many volcanoes are there? Very few, and very few places. So we cannot go directly on to that. Then there are another method is that drilling because for different purposes like for getting groundwater for I mean, for groundwater, we go up to 100 meters, but for getting oil, basically, we drill up to a few hundred meters also, 500 meters, 600, up to 700 meters also. So by drilling with broad cores and by observing those cores, we come to know about this layering, especially about the crust. I mean, the continental crust is a granitic in nature, that is CR, made up of silica and aluminum. It is lighter and the oceanic crust, when the drilling has been done on the ocean floor, it has found to be more of these Saima type, the silica and magnesium rich, heavier, slightly heavier than the continental crust. So this was observed on this uh, the core explorations. One more thing, since this is being organized by in Karad, Gaurav College, there is a nearby laboratory of Department of Works and VGRL, Borehole Geophysics Research Laboratory. They are doing this drilling. They have drilled up to probably a kilometer or more to know about the basement of the Deccan Trap. So when they have done all this drilling, they come up with the cores with different rock types. So in this way, we come to know about inside of the earth, but to a limitation. We know this up to a certain limitation with how crust is there. That's what we come to know with the help of direct evidence. So more important are the indirect evidences. So what are the indirect evidences? The most important is the P and S wave propagation. During the earthquake, the energy is released, vast amount of energy is released. It is in the form of waves, P wave, S wave, and L wave. L waves are the surface wave which causes the destruction. And the P wave and L wave are, they propagate inside the earth. So scientists have observed this propagation, P and S wave propagation, how they are propagating. And, when this wave propagate from one place, they've been recorded by different stations, seismographic station. I think this also been covered by PK Deshpande sir. So they record all this, and by doing the calculation, simple trigonometric calculation, at what time the P wave have received on a certain seismograph, and on the another station, the third station. So if you have three station data and arrival time of P wave as well as S wave, then we can back calculate what depth it has come up, come from. Accordingly, they have studied. Apart from that, there are other evidences like the Earth's magnetic field, the local gravity, because gravity is not uniform, even though we take in the example 9.86 and all those fixed values, but gravity is not fixed, in absolute terms. It varies from place to place. So, those minute observation, the minute variation, when taken together, we come to know about some idea about the inside of the earth. So, this is what I was telling about P wave and S wave. So, then the left is the propagation of P wave. Let's assume if this is the shadow zone, I hope the cursor is visible. So if this is the point of, say, earthquake happens at the zero, the P wave propagates and it passes through the crust and mantle, but it cannot cross the core, outer core to be specific. Okay, it get deflected from this outer core and then comes out from the other side. So it has a shadow zone from 103 degree to 140 degree. Okay, so this is the shadow zone for epicenter for P waves. If we take example of S wave for the same earthquake, S wave cannot propagate the outer core. Okay, P wave propagate through it, but it get deflected. Whereas in case of S wave, secondary wave, they simply cannot, pass through mm, uh, the liquid outer core. So obviously, how come we know about liquid core? Because outer core have to be of liquid because Otherwise, SWF would have propagated. So since it is not propagated, that means it's completely in liquid state. So this type of indirect evidences have helped us to know about the Earth's internal structure. Okay, so this is how basically the internal structure of the Earth is there. Outside is a very hot core. Okay, then out it is an inner core. Then this is outer core. Then you have mantle, and the crust is a very, very thin layer of crust above the mantle. So this is the internal structure of the Earth in a nutshell. I hope you have understood this because this is very, very important because without knowing this, we cannot understand the continental plate, how plate tectonics and how this continent moves. So moving ahead, now coming to the dynamics. Okay, so having understood the Earth's crust, crust, mantle, core, internal structure, it could have been the stationary, but it is not stationary. Why? Because the surface of the Earth moves constantly. I mean, there is a thing which is called a GPS, Global Positioning System, and there is one more thing which is called a differential GPS. I'm pretty, those who are from surveys, they know it in great detail. We can measure the position of a place with a accuracy in centimeters or even millimeters nowadays with the advanced satellite governed GNSS systems. So if we place on a location, if we put a station and if we record annually in those tectonics boundaries, we will get the deviation to a greater extent, and we can observe the movement of one place with reference to another place. Okay, since Earth is globe, so if one is moving toward north, which means other something has to move the southward way. So it's a reference wise movement. Okay, but that movement is being observed. So that makes the Earth is a dynamic planet. The lithosphere is divided this massive plates. It has been divided into tectonic plates. Earth as a crust is not uniform. It has different plates. Okay, and they literally float and moves on the mantle. As I said, previously, the crust is there and mantle is there. So crust, which a part, upper part of the upper mantle, this moves, right? It actually float and it moves over the mantle. And this has been observed by a scientist, and then they have proposed. So the continental drift theory we initially proposed by a scientist called Alfred Wegener. He said that the continents have moved slowly since Earth have formed. It is not remained fixed. It has been continuously moving. And he has given some evidences to this theory because, see, if I say the India is moving toward northwards by, say, 5 millimeter or say 10 millimeters a year, it cannot be observed by naked eye by crude method. And he has proposed it way back a century before. So therefore, he has come up with different evidences. He's come up with fossil evidences and geological evidences which support to this continental drift. So he proposed there was once a uh, a supercontinent called Pangaea. Now it has been established that it was not the once a supercontinent called Pangaea. There were multiple cycles of supercontinents. Like Colombia was one supercontinent, Rhodonia was there, UR was there. So there are quite different types of supercontinents when all this continental part was you know assembled as one part, one mega continent, and then separated. Hello. Okay, so it can be separate. It has get separated and again form taken together. Okay, so he has given with the recent example, the most recent supercontinent episode was the Pangea. So according to him, continental drift hypothesis stated that the continents had once been joined to form a single large supercontinent. Okay, so he proposed that roughly around 200 million years ago, this was the Pangea, okay, which is comprising of Eurasia, that is Europe and Asia, North America, South America, Africa, India, Antarctica, Australia, all taken together as a one single continent, supercontinent, which is called as Pangea, and the one ocean or mega ocean is called as Panthalsa. Okay, so and then he proposed that it get rifted. There is a movement. There was a breakage. Rupture has happened, and different because of the different rupture, this gets spread in a different direction and come to the present scenario. Like this, Asia is here, Europe is there. The here in the previous, you can see India is juxtapositioned by Antarctica. Now we see India is above the equator and Antarctica is down in the southern pole. So this was his proposal. So how come he come to know about this idea? So this is what he has proposed. 200 million years ago, there was a single landmass which is called a Crangia. It eventually breaks into two. It's called as the northern part is called as Laurentia, which is Europe and Asia, and southern part is called Gondwana land, where India was located. India, when I'm referring to India, is the peninsular India because that's the only India, Indian part was existing, in the older ages. Okay, so peninsular India was in the Gondwana land here somewhere. And after that, every continent start moving away. And this has resulted into, if we can now focus on this India, it was here up to 200 million years ago. 100 million years ago, it started moving away from Antarctica and Australia. Australia started moving towards the east. India started toward northward movement, and Antarctica started toward the more of the southern side. So eventually, this movement continues up to 50 years. India has reached up to Asia. Okay, with India have higher rate, India has reached up to Asia, and eventually up to 60 million years ago to 50 million years ago, India eventually collided with Asia, and this collision has given rise to what is known as Himalayan mountains, which is of great concern for us as a civil engineer because construction in Himalaya is a challenge. So, what evidences he has come up? He has come up for all this theory is the continent. You know, if we observe here, the Right. So this is South America. Okay, these are the its coastal line, and if you take its shoreline, continental shoreline, and matches it with the Africa, it matches to a great extent. Okay. Similarly, he has joined all these. No, he managed this Africa, this Madagascar and Asia and Antarctica. If you place together, they also matches. So accordingly, he has said that since these continents matches age by age, they must be together. One thing. Second and more important evidence that he has come up is known as fossil. Now, probably you all of you have must have seen the Jurassic Park. Okay, so this is a dinosaur movie. Once upon a time, there was dinosaurs, now extinct. So similar dinosaurs or any other creatures get, their dead bodies get preserved into the rocks, sedimentary rocks to be precise. And there is a science which studies all those fossils called as paleontology. So when paleontology is discovered, if the continents are at present, where they are now, like Asia is in the northern side, Australia is in the southern hemisphere, Antarctica is the southern pole. If it is the same, then the fossils which occur should be distinct because they will be locked by different land masses. But this is not the case. There are certain examples. For an example, Mesosaurus is a freshwater reptile here. It occurs on Southern America as well as Africa. Okay, so in Southern America, you get fossils of this Mesosaurus, and in the Africa also. Now, it's not possible to, it's a freshwater reptile. It cannot go into saline water because now in present day, the South America and Africa is separated by a vast Atlantic Ocean. It's not possible that this freshwater creature can go into saline environment and then come back and cross the Africa. So that's not one thing. Similarly, there were the plants, especially in the coal fields called Glossopteris langamopteris. Those plants get preserved in the shell and coal seams, especially in the coal seams. Those coal seams, when observed, they are found in South America also. They are also found in Africa also, India also, Antarctica also, and in Australia also. So in all these five, this Glossopteris is present. Now it's highly unlikely because from Antarctica, it's not possible to reach it to India, and moreover, there's this drastic climatic differences there in case of India, Australia, and Antarctica. But all these are occurring there. That means they were together once upon a time. So this is the second most important evidence that he has proposed was uh, the fossil. Third importance is the matching the rock type and structures. So there are, if you take this example of North America, the mountains or the rocks which are present in this side of the North America, they continue in Europe also. Whereas in between there is a vast ocean. But the same rock type, same lithology, same everything is same and it continues. Even in case of India and Australia, apart from there are the shoreline doesn't matches to a great extent. But the coal seams, Rajmundri and in this area we have coal seams. Of the coal quality is inferior. But the coal and the shale, if we try to race into Australia, we get a continuation. Apart from that, there is coal of superior quality, but you get complete continuity in the Australia also. So this type of rocks, continuity, their structures, folds, all get continued across the continent. And hence he proposed It, they were together once upon a time. Another evidence he said that glaciation. The glaciation is also a concept. Like we have the seasons, like we are facing here winter, then we will have the summer, then we have monsoon. Similarly, in Earth, there is also a cycle of glaciation and interglaciation. Currently, we are in interglaciation period, hence for the global ice cap is very less. Ice is found, glaciers are found only on the southern pole and other northern pole, and very high reaches like Himalayas, very limited. But 10,000 years is roughly a cycle. For 10,000 years, it will be a glaciation. The vast of the area will be experiencing cold climate. Okay. So this cold climate has been recorded by, again, the boulder beds, because when glaciers are there, when the glacier move, they create triash, these are called as grooves, scratched land masses. These land masses are created because when glacier moves, the bottom is boulders, and your glacier ice is having high, it has very high weightage. So when it moves, all these boulders scratches the whatever the bottom rock is there, and it creates a striation, these type of grooved surfaces. These surfaces are also observed all, they can also be imagined. For example, give from Maharashtra only. We have in Nagpur district called a place called Kampi. Okay, they all these have Gondwana sediments, and they have beautiful glacier patterns out there. Even in the Odisha, Talchir boulder beds, very famous. All these it indicates a glacial scenario. Now it's highly impossible to have a glaciation in a inside peninsula, center of the peninsula, because to have that, either the entire globe needs to be in the ice age, or the continent, that is peninsular, the peninsula India should be at the southern pole. So entire globe glaciation is not the case, but India was once at the southern pole. So this was another evidence that he has proposed. So glacier evidence he has been again explained here. In India, we have all these glacier evidences, and later India has moved up with all those signatures with it. That's why this glaciation triations is found in Madagascar, in India, and even in the southern Africa also, wherein it is not possible in the present day scenario. Okay. So he has come up with all those evidences. Okay. But he has faced a lot of criticism, a lot of opposition, because he have assumed the age of, say, in Earth to be 6,000 or 400 billion years only. But we know that the age of the Earth is 4.6 billion years. So he was not able to give justification to that one. But even more importantly, he could not explain how these plate move, right? We know now, mantle is there, convection current, and all those things are there. But in his 19th century, he was not able to convince them, the scientific fraternity, how this movement, what is the mechanism of this movement. He has given evidences for, they were together, but how this movement, he failed. So therefore, at that time, this continental drift theory was labeled as continental drift hypothesis. Later, it has been accepted. Yes, it is a theory. Okay. So now with the upcoming 20th century, we have come up with the different new evidences. So we can say this dynamic earth. And most of these evidences are with the advanced tech. Like for an example, the sea floor spreading, ocean floor is spreading. But since in the Wegener's time, it is not possible because sea floor is spreading at the bottom of the ocean floor. 3,000 meters below, we have evidences that ocean floor is moving. But at that time, in the 19th century, he will have only ship which will cross over. He will not be able to see through the water. But now we are able to do. With these evidences, uh, we have come up with what is known as plate tectonics theory. So sea floor spreading is one concept. Second, evidence is the heat within the earth creates convection currents like mantle. We'll see that. Third is the radioactive dating of the core sample. Okay, so we have done what is known as dating, age. How, what is the age of the rock? That has been also been done with the sea floor spreading thing, and then the magnetic stripping. Okay, we'll see this sea floor spreading evidences. So how this come up, how the sea floor spreading thing come into picture? Now, ocean floor is spreading. Basically, new lava is coming out and it's forming a new continent, and this formed new continent is moving away. Okay, again creating a fracture from which new lava will come, and it will cool and consolidate, form a new crust, and it moves away. This is called as sea floor spreading. But how come we know about this? This is all happened because of World War II. Okay. During the World War II, Henry Hess was a geophysicist and he was in charge of submarine. In world during World War, the task was to observe the enemy submarine and their activity. But after the World War, during the Cold War era, this submarines move and whatever the data they have collected is being analyzed during the Cold War time, post 1945. So when they analyze all those data, they come to know that just like on the continent, we have flat, then we have hills, ridges, and mountains. Okay. Similarly, inverted thing is present on the ocean floor also. We have ocean floor also, continental ocean flat is there, then ocean ridges are there, even higher greater height ridges are there, and from that volcanic eruption is also going. This is called as submarine volcanism is also happening. So they have observed that, and now they started. Once it has been discovered, the topic has been taken up by the scientific fraternity, and they started missions. And with this now ongoing continuous missions, they have now mapped 75,000 kilometer area of mid-oceanic ridge has been discovered, and it has been mapped. Now you can see these are the mid-oceanic ridges. He's been marked here. No? All these are mid-oceanic regions where from the new lava is coming and it has been spreading away. So here the most important is the mid-Atlantic region, that is from in between South America and Africa. And from Indian context, we have in Indian Ocean also we have a sea floor spreading event. Okay, so this is the 90 ridge spread from which the new oceanic crust is also being made. Now, this Hess proposed this process called a sea floor spreading, which I was saying. So he explained why sea floor was widening at mid-oceanic ridges when the molten magma from the Earth's core rises, not core, but mantle actually, from mantle rises and fills the ridges. So further work suggested that the sea floor was cycled back into the Earth to create ocean trenches. So it's a cyclic movement. Also, there were another evidences like the radioactive dating, the age of the rock. So when we age the rock, now we will find that from exactly at the near of the ocean floor, the uh, the age of the rock will be lesser, more recent, younger. As you move away from the mid-oceanic ridge, and if you dip, it will be more and more, higher age in it. It will be older and older. Okay, so this was been done. This has been also evidence that seafloor is spreading. And third is the magnetic reversal. Now, there is one more concept in the physics. It's called as polar wandering. That means polarity or north and south doesn't remain same. Like you must be knowing that the geographical north is different and the magnetic north is different. So this magnetic north and south, shifts. So this shifting is also been recorded by these rocks. So some of the rocks, from the ocean floor, some of the rocks will go normal polarity. Normal means showing north polarity towards the present day north. Okay, so normal polarity. Then after that there will be set of rocks which are on the both side, which will be showing reverse polarity. Again after that there will be another set of rocks which is showing the normal polarity. So this has been also been recorded. So these have also come to know that these rocks are new crust is being made, and of course Earth is not stable. So this is what I was trying to explain. So magma is there, and this newer crust from here it starts creating, and it pushing this continent part toward this direction and from this direction. And this way, newer and newer magma will start. So if during this eruption, polarity is normal, so it will record this rock will record polarity as normal. Record means the every magma has a mineral. Rocks have minerals, and the magnetic mineral align themselves just like normal magnet. If you hold it, will align in north-south direction. Similarly, magnetic minerals will align themselves. By observing those magnetic minerals, we come to know what is the polarity. So accordingly, this will be normal polarity. This second set will be probably a reverse polarity, and again the normal polarity. So in this way, we come to know about the spreading of the ocean floor. Now, with this entire discussion, we come to know that all this evidence provide a convincing case that sea floor is spreading is a real phenomenon. And not only that, the Earth's lithosphere. Now, lithosphere means the crust and the upper part of the upper mantle. Okay, crust and upper part of the upper mantle is called as lithosphere, and it is in motion. It is not stationary. Now, this is very, very important. This forms the basic of plate tectonics. Now, this is called a theory. It has been proven widely accepted. Okay, now with this plate tectonics theory, we come up with that the entire lithosphere. Okay, that means crust plus upper part of the mantle. If we take together Earth, it is divided into 12 major plates. Okay, 12 major plates and 20 smaller ones also. But major are 12 larger plate. Like for Indo-Australian, in our context, this Indo-Australian plate is a one major plate, even though India and Australia are quite apart, but they are resting on a single plate. Okay, so this is called as India and Australian plate. Okay, so these plates floats on more dense and fluid-like astronosphere. As I said, no, it floats, it moves. Okay, so these are the different plates and they have relative movement. Okay, with respect to one plate, another plate is in constant movement, whether they will be moving towards each other or moving away from each other, or there is a transverse movement, okay, slide past each other. These type of movements are there. Okay, so basically three types of these plate boundaries then are there. Okay, basically, as I said, either converging, diverging, or transform type of bonding. If the two continental plates, if they move apart, then newer magma will come out and newer crust will form. That means it will be constructive tectonism and constructive new landmass will be created. So this results into formation of ridges, rifts, volcanoes, more importantly. Okay, so these are called a divergent plate boundary. These landforms will be created on a moving key away from each other. If two plates, continental plates, move towards each other, they will collide. Okay, and when they will collide, they will form mountains, trenches, subduction zones, volcanoes, and earthquakes. Most important from civilian point of view, this convergent plate boundary results into gives rise to the major chunk of earthquakes that happen on the earth. Okay. And then third case is the strike blast, strike slip faults create will be there. And when, they move slide past each other, it will strike blast movement. And again, they also gives rise to the earthquakes also. Okay. So these are the three types of plate boundaries. One is convergent. Here you can see this is the, convergent plate boundary moving away from each other. Okay. And, like here you can see, so this is the moving away. And so this is the divergent plate boundary. It will give rise to the rifting, new crust will be formed, some new volcanoes will happen, but no destructive, like major destructive event will happen. Here, the one plate is moving towards and the another plate is moving towards each other. This is called as conversion and this is destructive. One plate will get destructive. Okay. Okay, out of these two, one plate will get destructed and some landforms will be created. And of course, there will be generation of earthquake. Deep focused earthquake or shallow focused earthquake will result in this region. Okay. And third is transform plate boundary. The best example is San Andreas Fault in USA. Okay, California state is subducting and it is moving past each other, creating of course civil engineering problem because the alignment of the railway tracks changes across the San Andreas Fault. So these are some of the things. Now, okay, how to remove this? Uh, okay, if you can tell me how to remove this annotation. Uh, okay, so anyways, leave it. If I have, okay, never mind. So now moving ahead, so these are the boundaries. So this is the first moving apart. So when these move apart, this type of rifting happens. Rifts will form. The best example is the East African rifts where rifting happens and the new crust is formed. Okay, so this is the East African Rift Valley. The second is important is the conversion. So there can be three scenarios. Plates are colliding with each other, but there can be three scenario. Why? Because the plates are of three types. One is, two types plates are there: continental plate and oceanic plate. Okay. If continental plate is there and oceanic plate is there, there will be a collision. So when the oceanic plate and continental plate collides, the denser oceanic slab. Because as I said, the oceanic plate is made up of Cl, and magnesium. So it's heavier, roughly around 3 specific gravity. So it is heavier as compared to continental, which is 2.7 or so. So when they collide, the heavier sinks into the asthenosphere, like lithosphere and then asthenosphere into the mantle, and this continental landmass gets elevated, abducted. Okay, so this results into continental volcanic arcs will form. Examples are the Andes mountains. So this is what is the convergent plate boundaries. I don't know how to remove this because If anyone can help me regarding how to remove this annotation. Okay, fine. Okay, now I'm able to do that. Thank you. So this continental this movement happens. Yes.
Yes, sir. Yes.
Yeah.
It's removed.
Yeah.
Okay.
So now with this movement, this subduction happens. This oceanic crust has collided with this continental crust. This heavier oceanic crust is going down. It also, when it goes down, as I said, the mantle is superheated. It is hot. So as this oceanic crust goes inside, it also get melted. Okay, partial melting happens, it generates newer magma, and those magma, since it is very, very hot and buoyant, okay, so it will try to reach up and try to attain the lesser pressure conditions. So it will move up and create this known as oceanic volcanic arcs. So volcanoes are called because when you have oceanic continental convergent plate boundaries. Okay, so this is one. Second is oceanic. If two oceanic plates collide, let's assume a scenario when a two oceanic plates collide. So if these two oceanic slab collides, both are denser. So whichever is the slightly more denser will move down, and this creates volcanoes and volcanic island arcs are created. Okay, so this type of thing happened when the one oceanic plate move create. This creates a trenches, deep trenches occur, and this type of volcanic arc inside the ocean are created because of this when oceanic convergent boundary is there. Third, and probably the most important from Indian context, is continental because this is what we are experiencing. Okay, so continental means when a one continental plate is collide with another continental plates. Okay, so when it happens, the weaker continental plate goes down inside the mantle. I mean, asthenosphere and then to mantle get consumed, and the other plate overrides or abducted. Okay, so this is the example. So this is the one plate. This is probably the heavier one, and this is the weaker one. So when the weaker plates it goes down, and it creates mountains. Okay, how these mountains are created, I'll discuss. But this create mountain, but this is not very simple. It creates mountain, but these mountains are made up of oceanic sediments. They are fragile. They are complex. They contain n number of structural disturbances like fold, fault, whatnot. Okay, all these complexities is fixed there, and as these complexities are there, these poses a great challenge to the civil engineering. I mean, if you want to construct anything here in the Himalayan region in our Indian context, it's big challenge. Okay, so that's why I was saying this is our case, okay, Indian scenario. Now, this is again explained with the Indian example only. So, India was again once, as I said, no, it was 70 years ago, it was near the equator or below the equator, started moving towards north. Okay, so this was the position in the 55 million years, then on 38 million years, 10 million years, and now present today. But how this has happened? India, means peninsular India, was moving along with this continental crust supported by the oceanic crust, of course, the oceanic crust, and it was floating. Okay, and it was moving towards north. But in between, there was a sea called as Tethys Sea. Okay, so Tethys Sea was there. So since this process, 71 million years to present, it takes huge time, millions of years are there. All this Tethys Sea, continuous sedimentation was going on because when there is an ocean, river will drain into it, it will come up with sediments, and they will dump all those sediments in the ocean. So similarly, this Tethys Sea was filled with these sediments, layered sediments, some unconsidered sediments, all those were here. And as Earth, this India started moving towards north, toward this Asian plate, Tibet. Okay, it eventually collided. But how it will collide? It has done all these ocean sediment, they get compressed. Initially, they get folded, and then they get faulted also. Okay, thrust faulted and get elevated. And that's what we see as Himalayan mountains. So Himalayan mountains are nothing but basically not all, but to a greater extent, the ocean floor sediments. Just imagine ocean floor sediment at the top of the mountain. This is what plate tectonics is. And this makes this region most unstable or seismically very, very active because this plate is going down. It's creating enormous pressure, enormous energy is getting stored, and as and when it gets chance, this energy is released in the form of earthquake. That's why you observe entire Himalaya receives earthquake on a very regular basis. Okay, so that's why it is very, very important. Third case is the transform boundaries, not very common. One only very important case is the San Andreas fault. As I said, you can see the field here. the shifting. Okay, so this type of San Andreas faults is there, and it creates, if your construction is cutting across this transform boundaries, then it creates a lot of problem. Otherwise, these are not very problematic thing except for minor earthquakes. Okay, this creates earthquake but minor. So these are the transform boundaries. How it moves? One plate is moving in another direction, another move slight passing each other. They are not colliding. They are not moving away. Okay, they are just slight passing each other. So because of the friction, some amount of energy gets stored and which eventually get released and causing some earthquake. Now, these are the cases how they can be a movement and all this. But basically, what are the causes and effects of this plate movement? Okay, once we understood what is plates, how they, plates are there, they get collided or get moved away or transform each other. Okay, in collision, there will be three scenarios. One is oceanic, creating trenches, oceanic continent. It will also be creating arches. Okay, and then continent, creating Himalayan mountains or mountain chains. Okay, so these are three. But how these continents are moving? That is the question that Alfred Wegener failed to answer. So of course, he tried to give some evidences like, moon pool and all these things, but that was not convincing. So what now we come to know is that how, since we are, say, take an example of India-Australian plate, huge, 10,000 kilometers at least in the length and breadth, probably 4 or 5,000 kilometers. How how on earth this will be moved? Who will move these large plates, even in terms of 5 meters or say 6 millimeters or 10 millimeters per year? Even that rate also not possible. So who is responsible? We come to know there are most important reason is what is known as mantle convection. Since I have said, that's why I discussed the structure earlier. Crust is solid, but the mantle is in plastic state, liquid plastic state. So it also creates convection. You must have seen, we know this is an 8th standard physics. Now, when you heat a container with water, the cold water initially get heated and then it gets convected up and colder water goes down and then this way cycle happens. So this is what happens inside Earth also. Okay. So this has been exclusively explained here. So basically, these uplifted mountains, volcanic belts, and arcs are found parallel to these convergent boundaries. Ocean trenches lie along the convergent boundaries, and this is the repetition for escaping. Yeah. So how this convection happens? So basically, mantle convection is the idea that there is a treadmill-like current in the asthenosphere, that means in the mantle, and that moves the crust that sits above it. No? Convection current is there. Just imagine if you have a moving some plastic material, and if you put a duster, like a wooden duster, and if you have mud which is moving, the duster will also move slightly along with that mud. Okay, muddy or clayey part. Similar thing happens inside the earth. Mantle moves. Mantle there is a convection current, and above there are whatever the resting continents are. They also move apart. In this way, movement happens. So this is what in detail they have given. First heat is there, magma rises, it get cooled, but while cooling it, the ridge get moved away. And when two plates move away, in this direction also there is another movement. So there will be collision and one plate will go down. So in this way, this convection cycle happens. Okay. Which is called as ridge push. That means this heated thing goes up and it gets heated, metal get erupted, new crust form, and it goes in the sideways. And then the sideways, when it goes, it gets pulled when it collides. Okay. So this is probably here, it will be very clear. From here, the newer the crust is formed, and when it get collided with at the other end, it get destructed. Simultaneous construction and destruction is also happening. That's why we are calling Earth as a dynamic planet. That's why Earth is the only living planet. Okay, no other planet have all these things. Okay, no volcanoes, no such active things, and because of these active things, only Earth is a dynamic planet. And because of that, only we are posing a lot of problem in construction. Okay, so this is in details. I will not go in much of the details. Slab pool and so just to nutshell, magma convection current. So this is probably if I don't know if it work or play or not. Yeah. So this is how it goes in terms of animation. Mantle plume, it's a molten material. This goes up. This mid-oceanic ridge forms. It moves away. This content goes down. And here, if you can observe, this newly constructed crust goes down and get destroyed. This is how Earth's crust moves, okay, on because of the mantle convection. So this has again been given. Also, there are certain things which we observe because of this plate tectonics. Newer landforms are created. basically volcanoes, mountains, and the trenches, deep trenches. These are created because of this plate tectonics. And again, these are very important from engineering perspective. Okay. So mountains form the convergent boundaries, continent boundaries causes mountains to form because of the collision of the two continent edges. This can also cause former coastline and marine fossils to be found on the mountain. See, Mount Everest is the tallest mountain, and it is made of limestone. Now, limestone happens to form in the ocean or at least in the basin. Okay, it needs some sediments. That means the water which is rich in calcium carbonate, its pH should change and it should allow the precipitation. So layer by layer, calcium carbonate will precipitate and form the limestone. Now this limestone is present at the peak of the mountain. Absolutely, there is no chance of having ocean at that height, but it is present there, which it indicates there was once upon a time this Mount Everest was the part of the ocean floor. Okay, so that's what I want to make the point. Another aspect is the rift, which are not in India. Rifts are more, of course, there are paleo rift. The older rifts are there, but not active rift. The active rift is in the Eastern Africa. Now, the African continent is splitting. Okay, so this rift happens when this magma comes up and it moves apart. There is third case also, which is called as hot spot. Trenches is also there. You must be knowing about when it can form on a convergent plate boundary. You have trenches, and Marina Trench is the largest trench formed because of this continental movement. Okay, I'm just rushing away because we have very limited time. Okay. So this is another example of continental trench formed because of the ocean. Some part get elevated and the other part get a little more deeper. So this deeper region is called as trench, and Marina Trench is an example. 11 kilometers is the depth from the water level. So entire Mount Everest, if we invert and put in still 3 kilometer will be water column. So this much is the depth of this subduction. Now, having said all this, now we come to know what is the important aspect, what is the geological events, or what are the phenomena or natural disasters in our present scenario, present FDP format. What are the different natural disasters that are caused because of this continental drift and plate tectonics? Because of this plate movement, what are the different disasters that we have to face as an engineer? First is the volcano. Volcano is the most common. If you know the country, Japan, Alaska, not country, I mean, Alaska is the US part, but Alaska, Japan, China, Philippines, all these have a lot of volcanoes because they are on the continental boundaries. The Japan is situated over two colliding continents, continental boundary. Because of this, boundary, oceanic and continental boundary, Japan is an island country and it is receiving, it has so many volcanoes. Okay, of course, volcanoes are accompanied by earthquakes also. So this is the first thing, very, very important. Second is the mental hotspots. What is that? I'll see. Hotspots are rising plumes of the mantle magma. So these are, so you see, if plate is moving and all of a sudden from this convection channel, if abruptly one superheated bubble comes up, it is called as hot plume, okay, hot spot or hot plume. So when this hot magma bubble comes up and it clears the continent, it creates hot spot. Different types of hot spots are created and different volcanoes are formed because of these hot spots. So hot spots are rising plumes of hot mantle magma. Okay, the Deccan basalt we have in Maharashtra Deccan basalt. It is thought and now established that it is formed because of one of such hotspot activity. When Earth was moving among 66 million years ago, Earth have crossed this such evolving magma. Okay, this hot magma, and when the crust moved, because this magma was very strong and have high buoyancy and high melting temperature, it crossed this entire Earth crust and started pouring. Okay, and of course, the movement of the Earth was movement of the India is also going toward northward. The hotspot remains stationary, and it has created flood basalt across the Maharashtra, some part of Saurashtra, Gujarat, and Malwa Plateau of Madhya Pradesh. So, reunion hotspot is the name of that hotspot because of which Deccan basalts are formed. Okay, and volcanic island chains and volcanic belts are also created. Okay. Third most important is the earthquake. Probably PK Deshpande sir have given a lot of emphasis on the earthquake. It was very, very important from civilian point of view. continent collide, I mean collision, wherever the collision plate is there, that means oceanic or oceanic continent or continent, it will result into earthquakes for sure. Apart from that, there will be another phenomenon also, but earthquakes are there, and there will be intermediate focus, deep focus earthquake will happen. All this we have seen, and earthquake is a major disaster. So this is the third thing. Of course, volcano will be formed, as I have said, when this plumes comes out, sea flow spreading, lava will come up. It is in the form of volcano. Volcano can also be created on the continent also when there is a subduction here. Because of this subduction, okay, because of this subduction here, okay, so here there is a subduction here, new magma will be created, and this, since it is very hot and lighter, it will come up and it will pierce the crust, and it will get into the newer volcano, and this forms it as a volcano belt. Okay, so this type of islands are also there. One of such thing is present in India. Only volcano in India is called a barren island volcano. It is of this type. Okay, but since it is in the Andaman Nicobar Island, and it is not of creating as such problems, so we don't have any problem from civil engineering perspective. Now moving ahead, hotspot, I think I have already explained with this is currently present. What I have discussed was the prelude. In the 66 million years ago, Rion hotspot was there, and India moved fast, created Deccan basalt. At present, there is an hotspot in the Hawaii island of USA in Pacific Ocean. As the plate moves, the newer and newer island get created. Okay, so this is the age of the newer and newer islands. But from these are not a threat from civil engineering point of view. Of course, earthquake is very, very important. Yeah, they will create a lot of faulting is there, and because of the faulting, the energy gets stored, and once it reaches a threshold, it rebounds, and entire energy is released in the form of earthquake. So this has been discussed. So I will not go in much of the details. So this is the epicenter of the earthquakes. If we plot the historical data of earthquakes and their epicenters, you'll clearly get the plate boundaries. Very rarely you will get an earthquake inside the plate. Most of the high magnitude earthquakes, greater than 7, occur either on the floor spreading, that is mid-oceanic ridges, mid-Atlantic ridges, like mid-oceanic ridges, or on the converging plate boundaries, or destructive plate boundaries. That's why you will see all these type of, so Himalaya, you can see, observe the Himalaya, it is huge earthquake frequency. Same is for this Japan, same is for this here you can see, same is for this. This is Japan, then this is Russia part, then this is Alaska. This is called as ring of fire. There are high number of earthquakes as well as huge number of volcanoes which are present in this region. So therefore, they are called as ring of fire, which causes a lot of trouble. Of course, the earthquake in the ocean creates tsunamis also. I think that has also been discussed by sir. So tsunamis creates a lot of problem to, especially in the case of Japan. Okay. So yeah. Now moving ahead. Now, with this, I think you have understood. We have discussed about the what is the continental plate, what is the plate tectonics, how plate moves, what are the evidences, what is the mantle convection, what are the different types of subduction, what are the different types of plate movements, convergent plate movement, divergent plate movement, transform. Even in the collision, also three cases: oceanic, continent. Having said all this theory, and also we have seen what are the different, disasters which are formed from this type of plate tectonics, like volcanoes and earthquakes. I think it will be incomplete without discussing one or two case histories which can be related with this plate tectonics and which is of Indian also. So I'll be giving an example. Of course, as I said, Himalaya, because Himalaya represents the collision plate boundary. Indian plate is collided with the Eurasian plate or Tibetan plate. The Tibetan plate was stronger, hence Indian plate is subducting. And all those sediments which were present in between these two, in the Pacific Sea, they get folded and faulted and resulted into what is known as Himalayas, mighty Himalayas. Okay, that's why presently there is a debate. No, Aravalli is the older mountain chain. So that's true. Aravallis are the older one, even though they are tinier, but they are older. Himalayas are way, way younger than Aravallis, okay, because they are formed because of this continental, this collision. and they are more complex. Complex in terms, there is no fixed mythology. There is a huge complexity in terms of rock types. After crossing few, meters away, you get entirely different rock types: sedimentary, metamorphic, mylonites, whatnot. You will get any and every combination, and that creates a lot of problems. So that's why I thought that it will be very, very correlatable with this topic. So Himalayan tectonics is what I have titled. So Himalayan geology or Himalayan tectonics is basically ongoing collision. Now, this is very, very important. It is not something which has happened in the past and now it is stable. No, present day also Indian plate is moving. It is being going down, the Tibetan, and there is the Himalayas are rising also. That's why the height of Everest is 8,848 meters as on whatever the year is, because it is still moving up. It is still rising. Indian plate is going down, and it is being more and more complex. That's why it is very, very important. It's ongoing collision that has resulted, since it's a huge, you can see the huge amount of sediments are thrown into folds and faults. It creates lot of structures which are main central thrust, main boundary thrust, main frontal thrust. These are folds and faults. They get initially the sediment get folded and then get faulted. One cycle, then another cycle, they further get folded and faulted. Okay, in this way, these are complexly get folded and faulted and result into a complex structural division right from Tibet, that is Indus, Yarlan, Sangpo, Sulsar, to the Sivalik Basin in India. Okay, so this is what Himalayan tectonics is. So basically, there are four broadly we can say zones: Tethyan sediments, like the ancient marine sediments, as I said. Then there are lesser Himalayan crystalline basements, some shield rock, like just like granitic rocks are there. Then high Himalayan crystalline, deep-seated metamorphic rocks like amphibolite, granulites type of rocks, and ophiolites, ultramafic mafic rocks are also present. Any and every sort of rocks is present in Himalaya. Okay, it's just that it is not predictable that you will get here this rock and there you will not get that rock. No, we cannot do. We cannot assume that even with the advanced geophysical techniques, geological techniques, or engineering techniques also. Okay, so that poses a lot of problems. So the active seismicity, Himalaya is very, very seismically active. Now, just probably in the last month only, we have got the seismic zones, revisited, and newer seismic zones have been declared, and of course it's continuously uplifting. That's why it is very, very important. More importantly, the rate of upliftment is varying across Himalaya also. The Ladakh region is having different rate, Nepal Himalayas have different rate of upliftment, and the Andaman side, or say Arunachal Pradesh side, have different rates. Okay, so that also makes system very, very complex. So to take an example, what are the things that as an engineer we came across? So these are very you know thing which is in the news probably a year or two before, I mean, 2023. This is Silkyara Barkut tunnel collapse. It's one of the tunnel which was being constructed in Uttarakhand. Okay, and it was very important, constructing for Chardham. They have thought to have do a construction. They have this was a 4.5 kilometer long. It will be tunnel and it will reduce the 20-kilometer road path. Okay, so that's why it is very, very important. But this tunnel collapsed. Okay, in the November month, trapping 41 worker under construction on the other side. Now there is one thing which is called as roof fall. When roof fall happens, you are working on your open face, one face, and then face collapse. That's one thing. And here what happened, they have constructed, they have moved away, they have moved inside, and all of a sudden, the back of their workers' side got fall. Okay, and it blocked. And they have attempted a number of things which was in the news. I'll not go in detail. All these failed to clear that. What was the cause? Why this? Because since this is a major project, it's not something which has been planned without having any thought. It would have, I mean, it is assumed that they have done all type of investigation, geological, geotechnical, geophysical, everything. And after that also this has happened. Why? Then a committee which is being led by Disaster Management Cell Nainital, it's a agency which works on this type of works, basically disaster management. They come up with a report. They now later found that this tunnel's location was in the proximity of main central thrust. Now, here is a catch. When I'm saying, or when they are saying it is near the main central thrust, it is an, what to say, referenced, assumed main central thrust. We cannot simply exactly map where there is a main central thrust. We can say, okay, here is the zone where there can be main central thrust. Okay, so on the established map, it is saying that it is in the near. maybe it may be crossing the tunnel also, okay, which is a major geological sheared fault zone. The sheared fault zone is a fault zone basically. Basic engineering geology textbook will teach you that when you are doing any tunneling, try to avoid the fault as much as possible. And if it is not avoidable, then at least see that the fault is not very active. Now you are going through a MCT. MCT is it spans from Ladakh to Arunachal Pradesh. It's that big. It's a huge fault. When we cross through it, what would have been? And if you see the rock type, it's a meta siltstone and phyllite, metamorphosed siltstone and phyllite. That means metamorphosed sedimentary rocks. Sedimentary rock, ocean sediments, which gone so down, it get metamorphosed and then come up. So this was the scenario. So they have now come up with the cause. There was a hidden loose patch of fractured or a weak rock. These are exact wording in that report. Okay, hidden loose patch of fractured or weak rock pocket was there, which they couldn't identify with the exploratory drilling also. They have done exploratory drilling. As just in any project, we do drilling also to just confirm our indirect method identification, that geophysical geology. We do direct drilling also. They have done this exploratory drilling. Still, they miss out this tiny loose patch of fractured weak rocks which filled, blocking those miners. And it is also been thought that when this structure, filled, it also gets filled with water. That's why the rescue was a disaster uh, uh, eventually eventually leading to we have to go for rat hole mining. If you know, mine has been created and rat hole miners go inside and then they rescue the 41 miners also. So this is one very, very important aspect. That's why this plate movement is very much. This was probably the location of uh, your most likely. I mean, this is not very confirmed, but likely a location of the tunnel. It is crossing through. Okay, so that's why it is very, very important. Now, coming to second case, okay, second case which is also equally important, and that is yeah, okay. Second case is the Joshimat and Tapovan submarine. Another Uttarakhand case. Here also on the 7th February 2021, a part of Nanda Devi Glacier bursted, which is on the upside of Joshimat is the town. And this flood have, flooded the rivers, the Dholi Ganga and the Rishi Ganga, both flowing side by side to Joshimat south. And the one Tapovan hydropower plant was there under construction. It also get destroyed. Okay. On 11th of January 2023, 2 years later, the Joshimat its floor, ceiling, and walls of the 723 houses is found to have cracks. Okay, you can see in the pictures. Subsidence is there, and land subsidence cases has been recorded in Hiroshima city. So this is there is one paper being published by Bara et al. In 2023, uh, titled "Sinking and Sleeping of Hiroshima Himalayan City." Okay, so here you can see this is the place of Hiroshima. Both sides there are rivers. This is one river, another river. We can see this NTPC powers now. This is the problem. We assume any and everything, and we do what as an engineer it is very, very suitable on a very standard landmass. That means in the peninsular India it is very, very okay scenario. But since we are dealing with Himalaya, a tectonically active zone, we need to be very careful. So what was the case? Joshimat itself is a problem. Joshimat town should not be there. In 1976, Mishra Commission has said that this entire township, tiny township that time, was on the old stable landslide boulder and debris. That means that was a landslide. That landslide gets stabilized and people started constructing houses over there. So it was first thing problem with Joshimat. Then they have prohibited any further construction. But of course, as in India, we just overlooked that recommendation. And now Joshimat is a quite a big city with a concrete, quite construction. And now when in 2009, this Tapovan Vishnugad hydropower in nearby vicinity started constructing, what they have done, their head race tunnel passes beneath the Joshimat. Okay, so it just crosses the Joshimat inside. And while for this doing this tunneling, they have blasted off quite a number of times. And while doing so, there was one village called Shelong village. This blasting has ruptured a huge amount of aquifer, creating a seepage of aquifer was around. No, the seepage was of intensity of 700 to 800 liters per second. Just, just imagine how much was the store of the water which is being gained, which is being getting drained instantaneously. And it is not about draining also. The water will be removed, the pores will be filled with the air or vacuum, and this will lead to subduction or to the subsidence. Okay. So that's why it is very, very important. Such incidents increases the hydrological instability and land subsidence incidence. This was the research work done by again these people. They have seen, they have mapped, and you can see a clear, more circled, textbook example of the land masses. You can see this is the weaker zone near to the Joshimat. Okay. Now this was still fine. It was still fine. But in 2022, Border Road Organization started construction Highland Baspa near to again Joshimat just to have the reduce the Badrinath distance by 30 kilometers. But while doing so, they use heavy machinery. That vibration again disturbed the entire already fragile system. Okay, so this heavy traffic and blasting for tunnel further destabilize the already fragile terrain. So therefore, of course, investigation is still on. But the negligence of complex geological rock setting formed in Himalayas because of this plate tectonics and drift, it needs to be honored to say at least if we need to avoid such disasters. Okay, so that's what the significance of this movement of plate tectonics is there. We need to address all these evidence and identify those features which are formed because of this type of tectonic movement, which is having active volcanism or active movement, because that will create a lot of problem. Henceforth, it is very, very important. Okay, so I will sum up with this. Uh, Thank you so much. This is Theri Dam again, a marvel of civil engineering. Same in Uttarakhand only we have this, but done with great care, and henceforth it is also an example what we can do. But previous to what we have when we have not dealt with the care resulted in. Okay, thank you so much.
Okay, sir. I just read the chat box, sir. Most of the
Yes.
participants appreciate your presentation. They are mentioned a very nice session. So this is a
Okay.
we can say that very greatly you are conducting this session. As a as a formally, I Rajendra Pawar, deeply thankful to our distinguished speaker, Professor Abhijeet Bhondave, Assistant Professor, Civil Engineering Department, Government College, Karad, for delivering an enlightful and insightful talk on continental deep 3D plate tectonic, the geological basic of natural disaster. Sir, your clearly explanation and practical insights greatly enhance our understanding of geological process and their relevance to disaster management and religion infrastructure. Before I close or wind up this meeting, I just allows that if anybody from the participants are interested to give a feedback or any question regarding the presentation, I just welcome all the participants for the question and feedback. So just you unmute
Good evening,
your
sir. Good evening, sir. Can I speak?
yes, yes, sir,
Yeah,
yes,
yeah.
sir, please.
Nice discussion, sir. We are grateful that you linked the geology and the civil construction very nicely. Grateful to you for sharing the two case studies, which were very, very informative and has enhanced our learning. Thank you so much, sir.
Thank you so much.
Very nice. Anybody from participant? Your review, your feedback, your questions always welcome. So
Yes.
okay.
Okay.
Sir, thank you for giving a time for us. And I just mention here, sir, available for us within some short notice and giving a great presentation. Thank you very much, sir. And I just clear here this particular session is completed. So thank you, sir.
Thank you. Thank you so much.